All right, now is the time for our final talk. This is by Josh Karlin from the Google Chrome team. Josh is a tech lead and engineering manager at the Google Chrome team. He's going to talk about Chrome's ad tagging and interventions. So over to you, Josh.
Hi there, thank you. So as described, I'm Josh Karlin on the Chrome browser. And my team focuses on preventing and intervening on bad ad user experiences, general anti-abuse, and the privacy sandbox. So thank you very much for inviting me to speak today. This has been a super informative conference. So a couple of years ago, my team set out to learn about advertising on the web and how and when the browser might need to intervene. During that time, we taught Chrome to not only filter advertising content where necessary, but also how to track and observe it for more precise interventions. And this work is all open source and documented. But we haven't had a chance to present on it, and I really appreciate the opportunity to do so today. So specifically, I'd like to talk about the ad-related interventions that Chrome is currently running, how our ad tagging works, future plans for CNAME detection, and an example of our anti-abuse work. So let's talk about the Better Ads standard. I really appreciated Eric's talk previous to this one, which was looking at sort of the types of content in advertising. And I want to talk about something slightly different, which is looking at ad formats. So there's this group called the Coalition for Better Ads. And they created a list of ad formats that are considered like sort of unacceptable for users. And this group is a coalition of trade groups, publishers, marketers, and agencies that put together research with 66,000 people from across the globe. Or rather, they performed surveys with 66,000 people, and they evaluated about 50 different types of ad experiences and asked them to rank them based on their preference. And in the end, they came up with a list of things that were the least user-friendly and suggested that these are things that should not be, and these are bad user experiences. And that includes things like where the ads on a page are too dense, so you just don't see enough content. Or the ads that appear as like modal dialogues on top of the rest of the page, or they're so large and they stick to the bottom of the screen, and as you scroll, you like just can't see much content. This is great. This is a list of things that a consortium, which even includes really large ad tech, says like this is unacceptable. So what do we do with it? Well, there's a system in place to have humans evaluate pages against this standard. And then pages that fail are informed via Google's Search Console. And then they're given time to fix the behavior. And if they don't, and the time lapses, then the site is added to a safe browsing list, which Chrome later ingests, and sites on that safe browsing list will have their ads filtered by Chrome. Sites can ask for re-review once they've corrected the offending behavior, or if they believe that they were incorrectly added to the list. All right, so that was sort of the initial intervention that Chrome took in this sort of advertising space. And we've done more sort of precision type things since then. So here's an example of our second intervention. And this one is related to drive-by downloads, which actually Eric sort of talked about downloading things from ads. And we discovered, and we were told about the fact that there are ads out there that, like, without user interaction, without any click or whatever, well, as soon as the ad loads on a page, we'll just download something immediately to the user's device, hoping that they'll later execute it. Like, they'll just see it in the folder, be like, oh, this has an interesting name. What is this? And they double click and bad things happen. So we thought, and thought some more, and we couldn't really think of any legitimate instances where ads should be downloading resources to the user's device, especially without any sort of interaction. So we created an intervention, and with it, Chrome will drop downloads from frames that are tagged as ads. if the user has not interacted with that frame. And this launched in Chrome 76. And finally, I'd like to talk about one more intervention that we have. And this one's called the heavy ads intervention. Here, we took a deep dive into better understanding the resources consumed by ad iframes. We looked at both network usage and CPU usage. When you hear about studies about like network usage of ads or about resource usage of ads on the web, it's usually about the total network bandwidth used. But Chrome actually has the ability internally to understand sort of the CPU usage of individual iframes on a page, which is really cool. So we took advantage of that. And so we measured CPU usage and just total milliseconds, and we measured total bytes loaded of ad iframes. And the results showed that the top 1 in 1,000, or the 99.9th percentile of ads, use a disproportionate amount of resources. In fact, that 1 in 1,000 ad creative uses 27% roughly of both network and CPU usage of all ad frames. So you might ask why. Well, you can imagine that you have an ad that's just simply poorly written, sitting in some kind of event loop, or it might have a giant image resource that it's displaying in a tiny little rectangle. There's a lot of reasons. Some of them might be just a large video that wants to display and on the side of a screen. That in the end, these things like cost the user money if they're paying for their network. It drains their battery if they're on mobile, and it can negatively impact performance, especially if you're just like hitting the CPU all day long. And these are, I also want to comment that these are things that the user is often unaware of. These are display ads, for instance, in iframes on the side of the page, and they have no idea why their phone's being slow or why it's heating up. They just know that they're browsing the web and things just aren't great, but there's no way for them to know why. And this is something that Chrome wants to intervene on. So what did Chrome do? We decided to unload ad frames that go above this threshold. That is the 99.9th percentile of resource usage of ad iframes. Now, I've got some numbers in here, like with the specifics, such as if the thread is used for more than 60 seconds by an ad iframe, or more than 15 seconds in any 30-second window, or uses more than 4 megabytes of network total. These numbers are actually derived from that 1 in 1,000, slightly rounded just to be an easier number to communicate. So what we do then is if a frame exceeds this threshold, plus some noise, we have to add some noise for privacy's sake so that you can't know exactly how many bytes something was or how much CPU it used. But anyway, when we unload the heavy frame, we send a report to the topmost frame in that ad frame tree. So we identify every a root ad frame and then all of its descendants and call that an ad frame tree. The root frame is told just before it's unloaded, hey, you're about to be unloaded because you exceeded the threshold. You have a moment to phone home and say I've been unloaded, and then we unload it. Now, if this was an error, because this is actually heuristically driven, then the user can either reload the page, which is kind of a natural response to fix things, and we won't intervene on reload, or they can go to their site settings and disable the intervention. We launched the heavy ads intervention in M85. And you can see on this side of the slide here that this is an example of what it looks like. It'll just say ad removed with some details. And I actually just anecdotally heard back from a friend the other day. They were thanking me for this because they were saying they're on a page on their phone, and the page slowed to a crawl, and they couldn't figure out why. And then suddenly 2 of these ad removes popped up, and everything was fast again. It was a CPU intervention. So it is working as intended. All right. So let's talk about what's going on under the hood and how Chrome is doing this. First, let's talk about filtering. This is done in a similar way to how it's done via web extensions. We ingest a filter list, like in this case, easy list, and filter requests that match it. It's the same tech that the declarative net request API uses, which was described earlier today. Let's see. One thing to note is that we don't use the CSS rules in the list, just the network blocking rules. We're considering the CSS rules. It's certainly interesting to us, but we are wary of the more expensive regular expression rules that we saw there. They seem like they would cause performance issues. But note, this was a few years ago. Maybe things have changed since then. Now, this was also talked about today, coincidentally. The filter list, especially at the time, this is 2018, 2019, was too big. It was something like, I don't know, at least in our internalized format, it became several megabytes. And that was too big to keep in memory on low-end mobile devices. And we wanted to keep it resident in memory all the time. So we wanted to shrink it. And we're happy to see, as mentioned in the earlier talk, that this actually is shrinking with lots of dedicated effort from the team over time, and that's great. But in 2018, we needed to shrink it, and we still do actually maintain this process where we just take the easy list and get it down to something that we think is small enough to keep in memory in all Chrome devices. So what we did was that we ran the filter list against every resource request made from every page load in the latest HTTP archive dataset. So HTTP archive these days, I think, has like millions of pages, page loads, and all the resource requests and the URLs for them. So we just run the filter list against that and count the frequency or rank by frequency, and we take the top 1,000. So the top 1,000 most popular or most hit denial list rules then become the core of our list. We then need to add to that all of the allow list rules, which is expensive and unfortunate. But there's no way for us to know which allow list rules are sort of like affiliated with which denial list rules. And if there is a way, please let me know. But it'd be great if we could just have the allow list rules that are needed with the given denial list rules we have. But we don't. So we add all the allow list rules, and that becomes our final filter list. And so how did this shrinking do? Like you're going to lose some capability when you do this. We're definitely missing a lot of rules. But what was the result of this? And it's really nice. So these stats are from 2019, but we shrank the list by 4x, which in turn doubled its lookup performance. And it still caught 99.9% of the resources that the full list did on the top 1,000 pages. So we were really happy with that. And I want to stress that the methodology that we have for compressing the list is publicly available. We run this roughly monthly. And the lists that Chrome has used over time are also publicly available. And that GitHub link is where our lists are. All right. So ad filtering is something that the folks in this conference are quite familiar with. But you may be less familiar with the notion of ad tracking. Here, the browser wants to differentiate between advertising and non-advertising content on a page without filtering it. And why is it useful to merely observe ads rather than to filter them? So that the browser can intervene on the user's behalf, but only when necessary. So take, for example, with heavy ads, we actually need to monitor what are ads on the page and what they're doing. And then once they exceed some threshold, then we intervene. And likewise, for the download intervention, we need to know what is an ad so we know when to intervene, which means that the ad has to load on the page, and you have to know which parts are ads and which aren't. So what we'd like to see is shown in the diagrams on this slide. That is, each frame and each resource request that is ad-related should be marked as such. Right? There should just be a bit on everything, and we mark each one. So for instance, in this example, we have this top.com frame. It loads a adloader.js script, which in turn creates a couple ad-related frames. One is this adtech.com frame, which then loads a foo.com ad. And on the right side, we have this, the loader also loads bar.com/ad. And then we have a third iframe, or a fourth iframe, I guess, called content.com, which is actual page content. and should not be marked. So our first sort of naive approach to trying to tag ad resources on a page was the simplest. Just apply the filter list to all the navigations and requests, like we would for filtering. And instead of filtering, just mark those resources as being ad related. Cutting to the chase, this didn't work well at all. And there's two major reasons for that. One is that not all ad frames have URLs, believe it or not. So it's impossible for a filter list to match them. They're often created with source stock instead of source, or as about blank frames, and then they get sent content to load from post message or some kind of attribute. The second reason is that it's not actually necessary for a filter list to enumerate all possible sites that might provide ad content. Most of the time, it's really only necessary to filter the loading scripts. Because once you filter the loading script, anything that it would have loaded from any of the possible ad destinations is automatically already filtered. Which means that the filter list is simply not exhaustive enough by itself to detect all ad iframes for our purposes. For instance, imagine this page that loaded adloading.js, which then created adtech.com iframe, which was blocked due to a filter list rule. Like you can imagine adtech.com being in the filter list. But that same loading script also created this other iframe, bar.com/ad. And let's just say that wasn't in the filter list because it isn't necessary to have there for when you're filtering. So then the question becomes, is there something we could have done to detect that? And thankfully, the answer is yes. The filter list gives us a really good start. You can think of it as like a root set of advertising content on the page. And it's the loading scripts and even some of the ad content itself that it includes. So what we want to do next is to watch what the known set of advertising content on a page creates. In other words, if a script marked as an ad resource loads resources, then assume those resources are ad related. And if a script creates an iframe, then likewise consider that iframe is ad related. So how do we actually go about this? Well, we're in the browser, so we get to peek at the JavaScript stack at the point that resource requests and frame creation is initiated. And if we see anything on the stack marked as ad-related script, then we consider the whole action to be ad-related. As you can imagine, this is expensive. And we've added a number of optimizations over time that I won't go into, but we have sped this up quite a bit such that it can be run live all the time. So this catches resources created by synchronous execution of ad script on a page. But what about asynchronous calls? What if that ad script, just to be sneaky and avoid detection, calls set timeout with a callback, and then that callback actually creates the frame? And then when the frame is created, when we look at the stack, all we see is this callback and no related ad script. Well, we monitor that too. It's what we call like an asynchronous stack. Effectively, what we do is every time a callback is given to the browser to be run at some future point, at that synchronous point, we look at the stack and mark the callback as ad related or not. And so if there was ad script that created that callback, then later when it executes, we can say, okay, whatever happens in this execution, this asynchronous execution later, we can say is still ad related. Okay, so we have a better method, but how does it perform? And that's always tricky to analyze. You need ground truth. And in this case, we're assuming that the filter list we use is ground truth. Like that, what we're trying to do is basically just be as good as our filter list would be when filtering as it is when tracking. And we also need some sort of data set of pages to test against. So in this case, we used web page replay to record the top 10,000 sites. Now, as an aside, if you replay with web page replay, I don't know how many people here have, but I'm sure some have. If you replay the same pages multiple times, even though they're coming from the same recorded set, you don't always actually have the same behavior on pages. It's not as deterministic as you might think. So we do have some baseline noise to consider. but this is what our experiment uses. So next, we load those 10,000 sites with ad filtering enabled with our filter list and keep track of the resource requests. So ad filtering enabled, load the 10,000 sites, and all that you should see is the stuff that's not ad content, and that's one set. And then we load those same sites with ad tracking enabled, but filtering disabled, right? And now we see all the resources, but we've labeled the set that are ad related. And then we remove the tagged resources. That tagged resources represents the ad stuff. So if you have the load without the ad stuff, then you should just have the requests that are not ad related. And those two sets should be the same, if everything is going well. And so we compare the two sets using the Jacquard index. And we see a Jacquard similarity of 99%. And in fact, it's 100% for the median page. So we've shown that our shrunken filter list identifies 99.9% of the ad requests, and that our ad tracking is identifying nearly the same set of resources as the shrunken filter list when filtering. So this is what gives us confidence that our interventions are working as intended. Oh, I should also note that the 99% number is after adjusting for 1% of baseline noise that I was talking about. Like for every 2 runs, even if they're like both blocking, then we see like 1% of noise and the difference in the request set. All right. So that's enough about ad tracking. Let's talk about other things happening in the browser. What about CNAME detection? Excuse me, need to cough. See if I can find a mute button. Sorry, wish I had brought some water. All right, so CNAMEs. Where that? Oh wow, I really do need water. Give me like 2 seconds. Oh no, there we go. My voice is coming back. All right, so CNAME detection. We know that some sites are using CNAMEs to avoid ad detection logic. We've plumbed the CNAME data through the network stack. So now it's just a matter of figuring out the right way to get it to extensions. It's not necessarily trivial, actually. In Chrome, the socket layer is unaware at connection time of what request it's making a connection for. It's a part of our optimization logic where we just have a ready pool of sockets that we can choose from when needed. But what it means is that it's tricky for us to create an extension hook with the CNAME data until after a socket has been selected, which means that an extension would be able to filter the HTTP request, but only after the socket connection has been made, which means that cookies would not go, the request would be blocked, but a socket connection to that destination would be made, and so an IP address would be known, like a socket connection would be there. It's not perfect, but it is very performant and should do the job. And the idea is to make this part of the declarative net request API. That is upcoming. Let's see. All right. And my last topic here. I want to leave you with an example of the abuse prevention that our team handles. So I'm sure you've been to a page and then realized that you didn't want to be there and you wanted to leave it and you hit the back button. But then you wound up on the page that you just tried to leave. We call this back button hijacking, and it's terrible. Some sites intentionally do this to trap you on their page, no matter how many times you try to leave. And how do they do this? Well, in one of a number of ways. But it's pretty straightforward. One is to just insert the page that they want you to navigate to over and over again in your history with the history.pushState API. That way, when you go back, it just pops off this push state or this the stack of pages and just keeps going to the ones that were pushed. And another trick, which is what I have a diagram here for, is to use redirects. When the user visits your site, it redirects them quickly to the destination site. And then when you go back, it goes back to the redirect page. So as an example, if you look at this diagram here, the user's on page A, and it has a link to page B, and the user's interested, so they go to page B. But all page B does is immediately redirect you with JavaScript to page C. So you're on page C, you're like, oh, I don't want to be here, I want to go back. You hit the back button, it takes you to page B, which dutifully takes you back to page C. And that just keeps going. All right. Now, you can escape this with a long press on the back button, which will show you a page in your history that will let you escape, unless that's been overwritten too, which is possible. But that's sort of advanced for many users, and we want things to work correctly the first time. So here's what we've done to address the issue. We've changed the behavior of the back button to go back to a page on the last site that you interacted with. So a page that uses JavaScript redirects or inserts a bunch of sites with push date will simply be skipped over unless you interact with it. So it's still not perfect in the sense that if you did interact with it, it can still trap you. But for the many cases where you realize that this isn't a page for you immediately, the back button will work. And that's it. Thank you very much.
Great. Thanks, Josh. This was really, really great. A few comments. First, I agree that bad ads are slowing the web down. So it's really great to see the Chrome team sort of addressing this. I think it's quite needed. The second is about the CNAME detection in coming in declarative net requests. That's really, really great to see, as you've sort of like already noticed in this event, like so many people talking about CNAME cloaking, and that is increasing over the years as well as so it's one of those things that I think is sorely needed, especially on having some kind of way to deal with this in Chrome. So it's really great to see this happening in declarative net requests. And speaking of which, there's also a question from Andre from AdGuard. Using the JavaScript stack trace to detect ads might be useful for ad filtering as well. Is it possible in theory that this could be also available in declarative net request in the future?
So that's something that we're thinking about, I have to say, because we agree that like it's unfair that Chrome gets it and the extensions don't. So we're trying to see if this is something that we can sort of lift out up into the extensions. Unclear, but it's definitely on our minds.
Yeah, apart from AdGuard, I can just say from our side as well, it is something that would be providing a lot of power to the extensions to actually block the ads that we're supposed to do. So that would be really, really nice for us to get. Apart from this, there's a few more that I had. One of them was, what kind of feedback or pushback did you receive from people working on the ad tech side when you were implementing some of these heavy ad interventions? Did you see any kind of like pushback or any kind of like any kind of vocal opposition to some of these things?
I would say in a lot of cases, ad tech is actually supportive. They don't want the ad ecosystem to be terrible for its users, and so I would say the majority of the time we've heard positive things. When we hear negative things is when the heuristics interact badly with folks, right? And then there are times that we simply cannot disambiguate between content and advertising correctly because of the way that our heuristics work. There are sites that will load content via ad scripts, and that's not a thing we can disambiguate. And so that there are definitely and this is more publishers than ad tech that are unhappy with that.
Yes, makes sense. And finally, where can people go to learn more on some of these things that you just mentioned?
Let's see. So the Chromium blog post, if you look up heavy ads, or if you look up or back button hijacking, or if you look up blocking downloads and ads, like if you just Google search any of those, you'll find articles coming from Google on that. If you are interested in our filter lists and how they're created, there's a link in the slides. And Also in the code, if you look up like add_tracker.cc, or sorry, .cc, you'll find like just the majority of the core of the engine for how we're actually doing the detection.
All right. We'll take the rest of the questions on Slack. It would be really great, Josh, if you can just take a look and answer over there. Once again, thanks so much for spending your time and explaining to all the people over here your work. This has been really, really fascinating. Thanks so much. And
thank you.